Welcome everyone to this webinar. This month we have actually two webinars beside the regular FEFLOW monthly thematic webinars. We are having today this release webinar for FEFLOW A0 Update 2, which is already available since 2 weeks ago. So in case you don't know me, my name is Carlos Rivera. I'm working in the HI as a global product specialist for FEFLOW, and today I'm going to show you a few things in the latest developments of FEFLOW A0. So for today's webinar, so it's about FEFLOW A0. So A0 was already released last November. So we have two releases. So release update 1, update 2. Today is about the update 2, which covers a number of maintenance tasks, but also we have the opportunity to introduce a number of new features. These features basically will be related to what we start in the last year in November with Supermesh repair and remesh. And we also have extension of the Well Manager editor. So I will be focusing the webinar today in these two features. But in case you want to know a bit more about the conceptual modeling or my cloud for FEFLOW and FEPES, just write in the chat and I can elaborate a few things at the end of the presentation. So 3D meshes, 3D super mesh improvements. So this is something that we have been working last month, so last year, intensively. For this, we have a partnership with GOD Solutions in France. So they are experts in meshing technologies. So we introduced GOD Solutions in FEFLOW the first time by the release of FEFLOW A0 in November. And we have been extending these workflows in this update, and in the near future, we will also have more integration between GOD Solutions and FEFLOW. So the motivation behind this is that, as you know, FEFLOW introduced the first version of unstructured meshes with FEFLOW 7 back in 2015, which worked quite well. However, they were limited by non-conformity of user data. So if you import your geological model from Leapfrog, OCAD, GeoModeler 3D, Petrel into FEFLOW, then if the data was not 100% clean, induce some so-called self-intersections, and then our generator was not capable to mesh it. So there was a lot of back and forward until the data was potentially repaired, but sometimes it was not the case. So there was no happy end. So the user ended up with another workflow. So this is a partnership, as I was mentioning, with GOD Solutions, a technology company tackle next generation of modeling challenge using advanced meshing. And the idea behind is, so we introduce methods to repair any improper 3D data in FEFLOW. Improper 3D data will be geometries with non-conformities, so polylines, so 3D polylines or surfaces. A surface could be a fall or could be a geological horizon. And this allow us to integrate new workflows in FEFLOW Supermesh and also introduce new possibilities to update the Supermesh. So this is offered through a new module that we call FEFLOW Advanced Module. This module is not Cell. This module is part of a maintenance concept that we have. So for those users with the FM3 license, Flow and Mass, and FNH3 license, the full FEFLOW package, if you are up to date with the maintenance agreement, so you automatically get exposed to this module, which allow you to work with GOD technologies in FEFLOW. So in the next releases, we are going to extend these FEFLOW advanced modules with meshing capabilities, but also could be other type of applications as well. So how it works is quite simple. So we have in FEFLOW a panel called Supermesh processing panel. And if you see my screen, here we have a number of faults which are not properly fitting the data. So you see they're above the topography. So in few words, what it does, the technology is repair the data. So it identify potential areas of conflicts, and then trying to look inside the model, it will verify this, it will identify the potential conflicts, and it will repair. That's the one step. And the other step is you can improve the quality of the mesh by retriangulate the surfaces, the inner or the outer surfaces. So this means that at the end, you have more possibilities to end up with a fully unstructured FEFLOW model. after the repair or remesh operations. So to demonstrate this, these two workflows, I have a number of slices, and the first one is about the remesh workflow. So you can call this remesh in FEFLOW, and so far how it works is it will remesh all the surfaces that you have. So it could be also seen a tool for simplified geometries or by refining also the geometries. So you see this surface, which is a topographical surface, which I'm going to use for the demonstration exercise later. I could keep calling this remesh operation or retriangulation in FEFLOW to end up with a more refined surface. So it will clean up some of the problems that I have and would also add a degree of a higher degree of details. I could do the opposite. Maybe the data, maybe I'm receiving a digital elevation model, which is quite well refined, and I don't need so many details. So I could simplify this by increasing the target's edge length in the remesh process to come with something more coarse. There are also new concepts in this framework. So there are the possibility to maintain or preserve what we call sharp features. So if you want to explain you this in simple words, you see this cube. So if I do not preserve the sharp feature, FEFLOW GeoD could basically run the geometry because there is no direct information to tell the algorithm that the surface will be preserved or not. You can decide this. So there are advantages or disadvantages. So obviously the major comment that will come here is that you might lose some details. Yes. However, the advantages is that you have a high degree of flexibility. So in cases which it's hard to measure, so you can increase the degree of flexibility and it will be potentially measurable, the case. The other workflow that we have is the repair workflow. This repair workflow is demonstrated here. We have a 3D domain, we have a fault. The fault is not fitting the domain. So we call the repair workflow, and the repair workflow basically throws everything that is outside and assure that the fault is fitting perfectly with the topographical surface, but also with the other outer faces of the domain. In combination with these two workflows, you can do a number of things. So this was already published last November, and then it came a lot of feedback from users, and one major feedback was, what about if I do not have a geological software to build these geometries? So it's a valid point. So we start implemented quickly in FEFLOW a number of tools to help these users. So now you can simply directly in FEFLOW create geometries like point, polylines, and planes. So here's the example of the plane. The plane can be seen as a tool to build simplified faults. So you can digitalize the trace of your fault, or you can provide coordinates. So you can directly do F2 and then provide exact coordinate of the trace. If this is the strike of the fault, you can provide inclination, the deep angle. Then you can provide also the information about the extent, so minimum and maximum elevation. And similar approach can be done for add Supermesh points. So you can provide 1 point or number of points, polylines. Many cases here in about geothermal modeling happening now in Germany. So people wanted to simulate inclined boreholes. So you can draw your own trace of the polyline directly into FEFLOW without the need to use external software. Bounding box is something quite interesting. So you can pass a set of surfaces which do not close a volume, and FEFLOW has a methodology to identify the bounding box, and we create a 3D volume for you so that you are ready to go for the meshing process. And playing is what I just explained. So we are extending. So actually there are more features than that. They are not published. They will be published later in the next release. And the other set of features are bounding box. You can extrude a surface or extrude the surface and build a 3D domain from the surface. So this is something that we have already implemented, but it didn't make it for this release of update 2. So we will have to wait for the next release. The other possibility, the other new feature that we have is the advantage to introduce new Supermesh elements afterwards, which basically means that if you have your 3D domain So you have built all your folds or your geometry, and you will add new information. So we introduce a new add Supermesh elements dialog where you can add new information always on demand and almost with no effort. So these geometries will be translated to Supermesh elements and can be used for creating a mesh, or if there are the conflicts with the existing geometries, you can repair it and then remesh it, or repair it and call the generator. By the way, generators, we have a new 3D unstructured mesh generator. Is powered by GeoD. We name it GeoD solution, so GeoD in the meshing panel. Beside GeoD, we have TechGen as before. And the major advantage of this is because we have everything in one single pipeline. So if you pass your surfaces, you can repair the surfaces, remesh the surfaces, and then we call at the end the GeoD 3D unstructured mesh generator. And since they use the same geometrical information or the same structure of the information, so it is speed up the workflow significantly compared to TechGen. So this is a first version of the mesh generator that we have. So you can see the number of options still limited. So in the future, we are gonna try to implement the number of options to control more the size of the meshes in heterogeneous mesh generations. So you might want to have small elements on part of the domain, or if you have polylines, to have more discretization around the polylines if these are boreholes. This is something that is not possible yet to be done with GeoD. It's gonna come in the next releases. But you can nicely combine this workflow with the TechGen workflow, so you can always achieve the maximum of the 3D unstructured meshes. So let me give you a few examples of how the workflow works. So I have been testing some cases around the world. So this is a case from Geoscience Australia. So they have a data set. So I have a number of data sets public available. If you want to know more about this, so we have a free training course, so you can use it to learn some of these different workflows. So basically here we have a number of folds. So I just simplify that actually more. We have a bounding box created by FEFLOW, and we can call GeoD to repair and then remesh. Or we have another example from the Peruvian Andes where the folds are quite irregular, so not really good. So we call first the remesh to do some cleanup of these data sets. So these are remeshed surfaces. And then we start doing step by step the construction of the 3D model. So adding the domain. Nicely, the domain does not need to be exactly coinciding with the fold. So we can, also happens quite often, so that you have a fold geological model which doesn't fit with the regional geology. So you would like to maybe discard some of this information. So we have a domain on purpose smaller than the fold system, so we can repair it. So we throw everything that we don't need outside, remesh it to clean up the data, the external surfaces and the inner ones as well. And then we end up with a FEFLOW model with some regional folds. Other example for those ones in Germany. So there are nice 3D portals from different governmental agencies. So this is an example of the Freiberg fold system. This is free available. The data is available in GoCAD format, but also in BTU or STL or object files. Again, take the data as it is from the portal, remesh it to clean out the surfaces, then add the box, repair to drop everything that is unnecessarily, and then we can call TechGen or GeoD 3D mesh generator to end up with a FEFLOW model with the folds. And you can add discrete feature elements if you want. Other example, where there is a video, we will try to publish the video soon. Again, from another portal in Germany, this time is from Bavaria, where we have a lower Bayer area, so neither Bayer. We download the surfaces, then repair the surfaces already, add the domain, repair. So you see the meshes are not so nice yet. So it's necessarily to call a remesh. We call the remesh. Now we have a nice triangulation in the outer faces, but also in the folds. And We can do the same with another domain. So that was a first test with a simple bounded box, now with a real geometry of the geological area. And so this is before and after the surface remesh. And you can end up with a FEFLOW model that looks like this and have all the different discrete features of faults implemented. And so in case you want to know more, I was mentioning there is this free self-paced course about the use of GOD and FEFLOW A0 Supermesh repair and remesh using the data from Geoscience Western Australia. Okay, next topic of this webinar is related to the Well Manager editor. You know, wells are important part of any FEFLOW groundwater project. So the motivation when we introduced a new editor was because it was difficult to handle many wells. So we have projects with hundreds of wells. So there is a lean-to parameter to create the wells, well BCs or multi-layer wells, but sometimes it reaches certain limits, especially in the case where you have already the wells and you would like to update some of the properties and you want to do it fast. So we create a new UI component, so a new dialog called Well Manager Editor. And the name say manager, so it's responsible to manage any type of well object. Either well BCs, multi-layer wells, borehole heat exchangers. Wells could be combined with flow and mass transport on flow and heat transport boundary conditions. Everything is quite clean through a tabular view. You can do some operations to queries, so you can loop wells based on time series, names, etc. It looks like this, so it's quite simple from the view. We actually on purpose make it really simple. So like a tabular view, so you can also import your wells, which come from Excel or any supported file formats. And in a couple of clicks, you have hundreds of wells in your FEFLOW model. It has some verified operations where it will tell you if there are conflicts. It will tell you if there are hints about well number 1 coincide with well number 10. So you will need to repair it and then adjust the coordinates. It has a section called extended properties where you can provide properties of multi-layer wells, but also define boundary conditions for the mass transport. So if you are doing some injection modeling cases, so you have a well BC linked with the mass concentration in FEFLOW, you can just do it directly from here. So don't need to assign the boundaries twice. So this is nice. This already exists since November. So we move fast and then did the phase 2 of this implementation, which is a Python interface. So for those who have been working with Python in the past or with C++ with the IFM interface, you know, we have a number of IFM methods implemented since probably more than 20 years. But we were still limited in one specific boundary condition called multi-layer well. So you can control, create or delete any type of well BC or any other boundary straightforward, but multi-layer well was still missing because it has a special implementation in FEFLOW. So we introduced a new class called Well Manager class. It's only supported through Python interface, not C++. This is a decision that we make it on purpose because most of the community was always responding and wishing Python implementations instead of C++. So it's a manager, same concept. So you can ask things. So give me the number of wells, delete all the wells, create new wells. You can create wells with flow or mass transport or heat transport combined. You can control any type of well from Python, so well BC, multi-layer well, borehole heat exchanger. Nice for those, we were talking a lot about unstructured meshes in the previous part of the presentation. So the other thing here related is that you can pass a polyline, you can pass a trace of the polyline, so which is described in through a tuple information in Python, and the well manager interface in Python will find what are the target location for setting the polyline. So it's obviously an approximation if your mesh is quite coarse. So it's recommended always to discretize it first so that the polyline will fit better the location of the web. So I'm gonna demonstrate some of these things in the demo. And if you want to know more about this Python implementation for the web manager, we have a new course. It's called Blended Course. Blended course means that you get the material to do yourself the exercises, but you also have the possibility to meet with a DHI instructor. In this case, will be with myself. So if you have active service maintenance agreement, so you can easily get this course with no additional cost. So you can register to this course and see more details and more about the conditions related to this blended course in the website. And with this, I would like to move to the live demonstration. For the live demonstration, I have prepared a simple example, but I think it will help to demonstrate some of the workflows because we don't want to make too large models. It's going to take a bit of time. So I start from scratch with creating a new FEFLOW project. It's a fully unstructured 3D mesh. Next, Supermesh import from maps. Next, and I will open the surfaces that I was showing before called topography. So this is the surface that I was showing in the PowerPoint presentation. So I could call a remesh to simplify and improve this quality. I will not do it because of time. I will just assume, okay, the quality of the surface is okay. And you see here, there is a new toolbar. If you don't see it, but you need to activate it, because it's new, under view toolbars, and then you have 3D mesh editor. This is the toolbar, which it will include new additional methods to create geometries. For now, in the next version, we have already implemented methods to select. So you can select surfaces, you can delete, you can invert selections, you can do more type of things with the bounding box. Okay, so it's talking about bounding box. So this is the tool. Add 3D Supermesh bounding box, and it just asks you one parameter, which is a buffer. So it calculates the size of your existing surfaces. It takes all. In this case, we have only one. And then it adds a buffer. It's an optional. So I'm gonna say also for demonstrations a negative buffer. So it's gonna cut part of my surface, if you see here. So it's gonna, sorry, here. So I have already a 3D domain with this, okay, but it's not really what I need. So this is supposed to be the domain for a deep geothermal system. So I need to go deep. So there is the possibility for now to change the dimensions of the bounding box. I think it's something that we need to also add more tools here to make it more visible. So you can edit the geometry. So these new geometries are added in the meshing panel. So we can edit them and say modify, and I will extend this to 5 kilometers. Just go up and down. Okay, so I would like to drop the upper part because my domain begins with the topography and then goes 5 kilometers down. So I'm gonna drop. You can delete any of these pieces because there are geometries, Supermesh elements. So I'm gonna drop this one. So now there is a hole here. So on purpose I do this because if I call now the repair method, it's gonna throw everything that is outside the closed domain. So I call repair. This will take few seconds. It takes him actually less time, but I'm dumping a lot of information. So I see also I have some debug informations. I have created now a domain with my final number of vertices is 1,884. So let's save this and let me put it somewhere. Supermesh and then say demo X. Okay, so this is the domain. So I can do a lot of things now. So, but let's try to improve the quality of the outer surfaces. So I will remesh it, and now we move from 1,884 to 2,729 vertices. So we are discretizing more the outer face. There is nothing inside, but we will add it in a moment. Actually, the generation or the workflow with UD are very straightforward. It takes a little bit more time. It's implementing after the repair, passing this into FEFLOW, but this is something that we would like to speed up. So now you see the quality is better, so we can keep saving the file. And now I say, okay, let's add a fault. So let me go to the top surface. So, and then I take this add 3D Supermesh plane. So draw a plane, so you can press F2 and provide a coordinate if you want. Exactly. So then comes this little dialog. So okay, let's give it inclination of 45. You can also say minus 45, and obviously it's gonna rotate the other way around. 45, and then okay. And then what you see, just cutting. So I could have extended laterally completely, but I just did it like this. So let's draw what we don't need with the repair again. Okay, so we have draw the outer surfaces. So you see now it's has been repaired here. So so now we are ready to mesh it. So let's go to the meshing panel. We have TechGen as usual. This is a second auction called GOD with the auctions mentioned in the presentation. Let's call it as it is. So you see that it takes a default length of 500. So what we have is we calculate what are the size of all the triangles in the Supermesh, and then we get the average value and we use it as an input parameter for GOD. So the mesh is ready. So we have here a plane. If I deactivate the hydraulic heads and the faces, I will see the plane which has been designed and the other information, so the topographical. So I could keep going back to the Supermesh, and if it's needed, so implement new faults. So let me see what I'm drawing. So we can add another one here, this time vertical, keep repeating the workflow, and then delete, remesh. You could also remesh it, and then introduce new faults with a better quality. So that's the whole idea of the workflow. Is really simple. And what we would like to do for the next releases is to make now the workflow runs for the repair runs for all the surfaces, but sometimes you might not need to do that. So we have all this information stored in the FEFLOW Supermesh different elements. So we could technically call the repair methods by in specific target surfaces. Now the surfaces are here. It's already repaired, so we can call GOD, and then we can see that the mesh is ready now. And now we have plane 1 and plane 2, and the two surfaces are crossing nicely. Okay, so for those, because I see there are many uses from the German community, so I will show you another example. So it is this portal from from different Bundesländer, different federal states. You have different information sites, so you can download the data here, and then so try to visualize. I know also in Canada there are also some available data sets, so it takes, the only drawback is that it takes a bit of time to visualize. So you see the different faults here. So the data can be, if you want to test the technology, you can download this, and then available of CADs or object files, shed files, or go BTK. This is something that I have already downloaded. So we can add it into FEFLOW. Need to find the information first. You can see all the different geological models that I have been testing. Nearby STL surfaces. So we can add the faults. That goes really fast because it's just one file. See that okay sometimes, but some cases like not really meeting well here. This will throw a self-intersection and by TechGen, and this one probably too. So you can call some remesh method. So we can say, okay, I know the values because its original model is quite large. So we can clean up the surfaces quite straightforward. Again, you are losing you are perturbating a bit the geometry of the original geometry, but it's something that you need to investigate whether it's worthy or it's acceptable in your case. And since these are, in my opinion, these are interpretations of some field data sets, so it's probably okay to sometimes not get exactly one-to-one. You can see here now we started with 42 vertices. Now we end up with 20,700. The surfaces are very regular. And then you can add the domain, so you can easily build your domain. Then you have your 3D domain with the faults, and then you can repeat the procedure. So I'm not gonna do that because of time, but what I can do is show you the final model. If you're interested on how to build the whole model from scratch, I can provide you a video that we recorded in the last weeks. So that's the full model with the different faults in FEFLOW implemented here with the real domain. You can see that's quite complex. What is nice and what I haven't tried, because the system also comes, or the data portal comes also with some geological horizons, we can also try it with this. Okay, so that was regarding to FEFLOW meshes. So let's do some stuff related to the well manager. In terms of the well manager, so how do you operate is quite simple. So I'm gonna open a new tab here and then start doing this together with you. So what I would like to do is, first we need to do basic operations. So we need to import the IFM and then define where the FEM files are and where I would like to store the new well, so new file. Then I'm gonna build a function to ask how many wells are in the file, and this is the well manager is starting like this. So .document points to this FEM document here, what is called well MRG 3D. It's a document that we can open also in the same time in FEFLOW, so that we can see what is there. It's not a good file. This one. No. So if I open the 3D view, so there are, if I can show here the number of wells. So we have one time constant and two transient well visits. Or we open the well manager editor from the menu edit, and you see I have 3 wells. So we can ask how many wells do we have? So most basic question. So we can then do this. Then just call this here below and then run it and see. So what it's gonna do is it creates a well manager object, and then basically get me all the wells, and then I would like to print them. So I have 3 wells, and these are the 3 wells that we have seen here in the view. Exactly. So the name and then the type is also shown. Okay, that's the more basic. So what else can we do is so we can leave actually this here. We could create a function to start creating new wells. So let's do this, and then I want to print a few things. And so the well manager, you need to use it once, and then when you complete the operations that you are doing, you need to throw it away or you need to reset it. So you can call this create well manager object as many times as you want. So I create here another, and it requires snap distance because not necessarily the wells are fitting the location of the nodes. And clear wells, what it's doing is going to delete all the wells. So we have 3 wells, so we're going to delete the wells. And first thing that I would like to do is create a new well. So this well will be entered like this. So well manager method create well, and requires to know what is the type of the well. This is a MLW is a multi-layer well. So I'm creating a multi-layer well, and this multi-layer well it's empty. So it's not, because it doesn't know about properties or doesn't know about location. So it creates a placeholder for a multi-layer well. And then we start putting properties. So we are going to put 2 properties. The first is the type, and the second is the name. So we're going to put put property value, well type, and I'm telling this is a flow multi-layer well combined with the heat transport boundary condition. And it's going to have a name called created well from top bottom. So not very not very difficult. That's one approach. So I'm creating a multi-layer well, and so then the question is, so where is actually putting the well? So per default is using the centroid of the domain to create in the center a multi-layer well. So if you have another well exactly in the right location, it's going to create a conflict and it's going to tell you there is another well there. So next, let's create few multi-layer wells, this time by giving the IDs of the edges. So you need to know the edge ID. And if you have selections stored, then you can easily get this. And these are different wells. So we're gonna introduce the different wells by with this method. So we're gonna create names and then name it multi-layer well from item libs and just add a different ID. And the next step is to create the other method is create a multi-layer well using a polyline. So it works with global coordinates. It's a bit different how the other functions in FEFLOW work. They always work with local. Now we work with global because you normally know the real coordinates of your well, so you don't want to make a translation in coordinate systems. And this is going to create wells, multi-layer well type. And instead of receiving the IDs of the edges, this time gets a Python tuple with the coordinates X, Y, and Z coordinates. And at the end, we are going to put some, again, name to be able to understand. And if I leave it like this, nothing is going to happen. I need to apply. And the multi-layer well has its own operation called the well manager has its own operation called apply operations through, and this is gonna give me the list of errors if there are any. And we can also call the function again because we want to see. So I'm gonna save a file, fem out, and the file is like this. So let's delete this, and then if I run it first, so the result, so this is what is printed in the function here. The result is a fem file which does not have the 3 wells that we saw before because we are cleaning, and has only multi-layer wells. So if I go to the fem document, open, and then I see German time is 7042, this is the right fem document. It's clear, and then now I open the well manager with Control W, and the original 3 wells are not there. We have created a well from top bottom. That was the first. Then 3 multi-layer wells with the IDs and 1 multi-layer well using the polyline. So in the case where the wells are horizontal, so they obviously FEFLOW in the GUI show you the coordinates. In the case there is a polyline, so we don't know what is the X, or we know, but we are not visualizing this in this tabular view. So with this, I would like to go back to the presentation. I have 1 slide more because you probably now are curious, okay, what next? And I like to actually give you an overview what is coming in the next months. So we have here things that they have been already developed. So we are working in more things. Still, we have a number of months to go before the November release. So well manager, I show you now the well manager. I see there are some German users, especially one who was asking me this. So we introduce now the possibility to group wells, and the groups could have rules, and there is a rule called open loop. So this has been recently implemented, actually last week. So you can group the wells. The groups could receive a rule. And this open loop is basically modeling a geothermal open loop system. So we are gonna get rid of this all implementation with a plugin, and this gives us a significant degree of speed, a significant performance improvement, because the calculations are really directly done by the FEFLOW kernel. And the idea behind is also to extend all these rules, so we can have also possibilities to activate or deactivate wells in one single shot without the need to delete them from the project, which is quite nice. We have also introduced new concepts in the observation point dialog, so you can also group your observation points. Quite nice, because if you have different aquifers or different layers, so you want to see everything in a group. Inspection tool has been also reviewed, so we have new ways to work with inspection tools. So for large model, there was always a problem when you move the inspection tool from A to B, and it was hanging along the way. So now you avoid these mechanisms that you can, with a combination of keywords, you can activate or deactivate the inspection, basically. We have some automatic workflows for cross-section. So normally you draw a cross-section line and you need to say, okay, right-click, open cross-section. So now we have some default that automatically open the cross-section. In terms of 3D meshes and 3D super meshes, so we keep adding more tools. We have many more tools already developed to create geometries directly in FEFLOW. So you pass a surface, and now we can extrude the surface to create a 3D domain. So it's the second version or the advanced version of the bounding box method that I showed you today. Selection methods in 3D Supermesh, methods to delete. We are also, it's not done, but we are working on that. So, and we will be working in the next months or weeks, methods to digitalize. So you might want to draw your fault, snap into a specific coordinate which already exists. So this is something that is coming. And for those working with 3D and structure meshes, so it was always a problem to look the things in 3D. So we are finally revealing a new ortho view where you can nicely see visualize your 3D and structure models looking in a cross-sectional view or in a horizontal view. Okay, thank you for participating in the webinar. So before I conclude, so there is still one thematic webinar coming later this month. Is related to unsaturated flow modeling. So I'm going to show a few things about Richard's equation in FEFLOW. This is our last thematic webinar. Then there is a break in July. And for the time of the next webinar, I'm going to show you the next webinars from August until the end of the year. So thank you for participating, for your interest in FEFLOW and in these thematic webinars. So thank you for participating. I would like to see you in the near future through the different sessions that we have. And with this, I would like to wish you a great day. Bye.